Hello everyone, welcome to this lecture. So, in this lecture we will discuss about the characterization for perfectly secure Byzantine agreement in incomplete graphs. Okay. So, we had already seen that if we are interested to design a perfectly secure Byzantine agreement protocol in a network which is modeled by a complete network, complete graph, then the condition n greater than 3t is necessary. So, k sub n here, the notation k sub n, it denotes a complete graph with n nodes. We now want to find out the necessary condition required to design a perfectly secure Byzantine agreement protocol in incomplete graphs, where there could be T Byzantine faults. So, the characterization or the necessary condition is the following. It can be shown that perfectly secure Byzantine agreement in an incomplete graph, where we have n nodes and up to t of them could be Byzantine corrupted, is possible if both the two conditions are satisfied. The first condition is that n has to be compulsorily greater than 3t, and the second condition is that the vertex connectivity of the underlying graph, underlying network has to be at least 2t plus 1. So, let us first try to understand what do we mean by the vertex connectivity of a graph. Okay. I am sure people who have studied graph theory, they will know what is vertex connectivity. So, this vertex connectivity of a graph G is denoted by the notation kappa of G, and it denotes the minimum number of vertices which I have to delete from the graph, so that the graph either becomes a disconnected graph, or after deleting those nodes, those vertices, I am left with a graph which has only a single node left. The minimum number of such nodes whose deletion either leaves a disconnected graph or a graph with a single nodes is called as the vertex connectivity of that graph, and that is denoted by the notation kappa of G. And it is easy to see that kappa of G will be a quantity in the range 0 to n minus 1, 0 if the graph G is already disconnected, that means I do not have to delete any other node to disconnect the graph G, or the vertex connectivity could be n minus 1 if the graph G is a complete graph with n nodes, because in a complete graph of n nodes, where there is an edge between every pair of vertices, even if I delete up to n minus 1 nodes, I cannot disconnect the graph. I can only ensure there that I am left with only a graph consisting of a single node if I delete n minus 1 nodes. So, pictorially, let me demonstrate the vertex connectivity with few examples. So, in this graph the vertex connectivity is 2. This is because, for instance, suppose I delete the nodes C and F, then this node G will be left alone, because as soon as I delete the node C, this edge between C and G vanishes, and the edge between G and F vanishes, because if I delete the node F. Okay. Whereas, if I just delete any one node in the graph, say for instance, if I delete only the node C, then the graph still remains connected, because from G I can still reach to F, I can G and through G I can reach to every other remaining nodes in the graph and so on. The vertex connectivity of this graph is 0 because it is already disconnected. And this is a complete graph K 3. So, its vertex connectivity is 2. If I just delete C, say for instance my graph remains connected, and if I now remove the node A and the edges incident with the node A, I will be left with a single node graph. So, that is why the vertex connectivity will be 2. Now, let me introduce a problem called perfectly reliable message transmission or the PRMT problem, and this will be useful later while understanding the characterization for perfectly secure BA in an incomplete graph. So, we are given here a network, communication network, and we have a sender S and we have a receiver R, and they do not have any pre-shared information. They do not have any pre-shared information, but they know the full network topology. Okay. Also, it is guaranteed that apart from the sender and the receiver, up to T nodes in this network could be under the control of a computationally unbounded Byzantine adversary. Our goal is to do the following. We will first abstract this underlying network in the form of a collection of wires or channels between the sender and the receiver. So, wires you can imagine as some kind of communication channels, and these wires are disjoint. So, W1, W2, W3 are disjoint wires. So, how do we get 3 wires between S and R here? So, how many vertex disjoint paths we have? Between S and R. So, we have the path S to A and A to R. We have the path S to D and then from D to R. Now, you might be saying that there are 2 more paths S, B, A, R and S, C, R. But the point is that if the node B gets compromised, if the node A gets compromised, then any communication which happens between S and R and which goes through this intermediate node A will be completely under the control of the adversary. So, that means whatever sender communicates through the path S to A to R and whatever sender communicates through the path S to B and then B to A and then A to R, both these paths are compromised if A gets corrupt. Right. So, that is why what best we can do here is we can just assume that we have 3 vertex disjoint paths. Indeed, we have 3 vertex disjoint paths. So, the paths S to A to R and the path S to B to A to R, they are not vertex disjoint, they share a common node, namely A. So, that is why both these paths will be abstracted by a single wire W1. Then the path S to D, D to R will be abstracted as wire number 2 and the path S to C, C to R will be abstracted as a wire W3. Okay. So, since up to T intermediate nodes could be corrupt among these n wires, okay, not n wires, whatever is the number of wires between S to R up to T wires or channels, whatever you consider it, could be Byzantine corrupted. That means, the communication over those T channels is completely under adversary's control. Adversary can do whatever it want over those T channels. So, it can simply block the communication over those T channels or it can change the contents over those T channels and so on. The exact identity of the T channels which are corrupted by the adversary will not be known to the sender and the receiver, because neither sender nor receiver will be knowing the exact identity of the corrupt nodes in the network. So, that is why they will not be knowing beforehand which wires are going to be under the control of the adversary. Now, what is the goal here? What is the goal in the PRMT problem? So, we are given this setting, a network which is modeled by a collection of vertex disjoint wires between a sender party and a receiver party, and sender will have some message from some message space. We want a mechanism, a protocol which would allow the sender to send its message in a perfectly reliable way to the receiver. That means, we need a protocol according to which sender should send some information over these wires, so that even if up to T wires the communication over those T wires is changed, is blocked in whatever way, receiver should be able to recover back the message, and this should hold even if the adversary is computationally unbounded. Okay. So, let us see a very simple PRMT protocol. Imagine there exists 2T plus 1 wires between the sender party and the receiver party. So, for instance, let us take T is equal to 1. So, we have 2T plus 1 here, 3 wires between the sender and the receiver, and suppose sender has the message M, then what the sender can do is the following. It simply send the message M along the first path or the first wire, send the same message along the second wire and send the same message along the third wire. Since one of these 3 wires could be Byzantine corrupt, say for instance the second wire is Byzantine corrupt, the adversary can change the copy of M to M prime when it is going over the second wire. The receiver will not be knowing which wire among these 3 wires have delivered the incorrect copy of M, but what it knows is that since among the 2T plus 1 wires the majority of wires are honest, the majority of wires are honest, and when I say honest, I mean to say not under adversary's control. It knows that it will receive at least T plus 1 copies of sender's message, and there could be at most T messages which are different from what sender has communicated. So, it can simply output the message which has been received T plus 1 times along T plus 1 different wires. That is what is going to be the sender's message. Okay. So, that is a very simple PRMT protocol. Okay. Now, coming back to the characterization for perfectly secure BA. So, our characterization was that in an incomplete graph, if at all you want to design a perfectly secure BA protocol, then that requires n greater than 3t as well as the vertex connectivity of the graph to be 2t plus 1. So, I will be just showing the sufficiency proof here. So, this characterization is both necessary and sufficient, because this is an if and only if condition. So, I will show that if the condition n greater than 3t holds, and if the vertex connectivity of the graph is at least 2t plus 1, that means both these conditions are there, then there exists a perfectly secure BA protocol in an incomplete graph. Okay. Even if up to t nodes or t parties out of the n parties are Byzantine corrupted. And the proof is very simple. You take any perfectly secure BA protocol over a complete graph with the condition n greater than 3t, say the EIG protocol or the phase king protocol, whichever protocol you want, where we have a complete graph. But now we want to design a protocol over an incomplete graph. So, we can't run the EIG protocol or the phase king 2 protocol over an incomplete graph, because in the EIG protocol there are instructions that every party sends some message to everyone else. But in this incomplete graph, we do not have a direct channel between every pair of parties. So, what we do here is the following: we run the existing protocol over the complete graph with n greater than 3t, and whenever as part of that protocol a message is supposed to be communicated from the party p sub I to party p sub j, we check the following. If in the incomplete graph the edge pi pj is present, then it is fine, send a message directly. That means send a message directly means pi send a message directly to pj over that channel. But if the channel from pi to pj is not there, if the edge p sub I, p sub j is missing, then what we can do is the following. Since we know that the vertex connectivity of the graph is 2t plus 1, then by invoking the Minger's theorem from the graph theory, which states that if your graph is k connected, then there exists k wires between every pair of nodes in the graph. So, that means if the vertex connectivity of the graph is guaranteed to be 2t plus 1, this means that between every pair of parties pi pj, there are at least 2t plus 1 wires. So, if pi is supposed to send any message to pj as per the protocol pi sub 3 ba, pi sub ba, sorry, and if the direct channel from pi to pj is not there, then what pi can do is it can invoke a PRMT protocol, which we have discussed just now, and send that message to pj. Okay. So, for instance, if we take this incomplete graph here and say we take t is equal to 1, what I am saying here is that suppose in the BA protocol U1 is supposed to send its message to U3, but there is no direct channel from U1 to U3. But how many wires are there between U1 and U3? I have the wire 1, namely the path from U1 to U2 and U2 to U3, that is wire number 1. I have another wire from U1 to U3, namely the one going through the intermediate node U4, that is wire number 2. And I have another wire between U1 and U3 going through the intermediate node V2, let me call it W3. There are 3 wires. Now, what U1 can do is, it is supposed to send the message M in the protocol pi BA. What it can do is, it can trigger the previous PRMT protocol. So, it will send the message M along this wire and this wire. Say for instance, the node U2 or the party who is controlling the node U2 is Byzantine corrupt, that means the wire W1 is corrupt. Then it can forward M prime instead of M, but the wires W3 and W2 will forward M to U3, and U3, the party who is controlling U3, who is sitting over the node U3, will be able to recover M, and then it will proceed in whatever way it is supposed to after receiving the message M from the node U1 according to the protocol pi BA. So, basically what we are saying here is, if the vertex connectivity of the graph is at least 2t plus 1, right, if the vertex connectivity of the graph is at least 2t plus 1, then we can emulate a complete graph, we can emulate a complete graph Kn over an incomplete graph. That means, even though physically we do not have a complete graph, we can imagine that we have a virtual complete graph, where every communication between Pi and Pj can be emulated through a PRMT protocol, because there will be at least 2t plus 1 wires or vertex disjoint paths guaranteed between Pi and Pj. And now, if we have a complete graph, either physical complete graph or a virtual complete graph, we know that we have plenty of BA protocols which are perfectly secure if the condition n greater than 3t holds, which will be guaranteed because of the first part of the necessity condition. Okay. So, that shows that you can design a perfectly secure BA protocol, you can run a perfectly secure BA protocol even over an incomplete graph if you have sufficient connectivity in the underlying network. Now, that shows the sufficiency proof. Okay. So, whatever we have shown here is the sufficiency proof here. Because we showed that if these two conditions are guaranteed, then they are sufficient to design a perfectly secure BA protocol. Now, we will argue about the necessity of the condition 1 and condition 2. That means, if we have an incomplete graph and if any of these two properties are violated, okay, if any of these two properties are violated, then we want to argue that we cannot design a perfectly secure BA protocol in the underlying graph. So, imagine first that the first condition is violated. That means, instead of n greater than 3t, we have the condition n less than equal to 3t, and say my graph is having the network connectivity which is at least 2t plus 1. That means, the second condition is not violated, it is only the first condition which is violated. then the contradiction we get here is that if at all we have a perfectly secure BA protocol in an incomplete graph with the condition n greater than n less than equal to 3 t, then the same protocol will also be a perfectly secure BA protocol in a complete graph with the condition n less than equal to 3 t. But we know that in a complete graph we cannot have any perfectly secure BA protocol with the condition n less than equal to 3 t. That means, the existence of pi sub BA which we assume to exist is wrong. Now, what about the necessity of the second condition? Well, the proof is slightly involved here. So, I will not go into the exact proof, but the idea there is that if the vertex connectivity is not 2 t plus 1, then we can show a sequence of inconsistent executions of the assumed Byzantine agreement protocol, and we can compose them, and then we can arrive at a contradiction that at least one of the properties of the assumed BA protocol is violated. Okay. So, I will not be going through the complete proof, but if you are interested you can refer to the textbook by Nancy Lynch. Okay. With that I end this lecture. Thank you.